for a stop. Okay. So what actually happens is that whenever there is a certain kind of periodic movement going on. Now, for periodic movement, what is periodic motion? Do you remember that?
Yeah, it keeps
Mm,
repeating itself at
exactly.
certain time intervals.
Yes, exactly. At a certain regular time interval, it will repeat itself within its own till the time it gets lost by the air friction and it stops totally, right?
Yeah,
Now, we know that for any kind of motion, the acceleration is proportional to the displacement, right?
yeah,
Because with increase in displacement, acceleration will also decrease, and that happens from a fixed point that is in motion. What if there is a mass in the end of that displacement occurring? Then what other things start working on that mass? Like suppose I have a spring and I'm attaching a mass to one of the end of the spring and just fixing one end of the spring. What will happen then?
the mass will move.
Yes, if I just apply some force on it, then the mass will start moving and it will move in a periodic motion till the time it comes to a stop, right?
Yeah,
Now, when there is such kind of movement happening which is periodic in nature and which will stop after a certain amount of time due to the action of the uh, friction, and that time the simple harmonic motion gets combined with the force and particularly gives us a new kind of harmonic motion which is known as damped harmonic motion. Are you getting the point?
right, yeah.
This is one kind of a situation where some mass is hanging from a certain kind of object and there it is experiencing a periodic motion. This is one of the examples. It can happen anywhere. It can happen in any situation, but yes, particularly these kind of situations. Now, whenever we are talking about this, there is a law. The law's name is Hooke's law. Okay.
Right, yeah.
Do you remember Hooke's law?
Yeah, it's a spring and it keeps oscillating or something like minus or delta x into k.
Yes. Negative kx. That is for the spring force, right? That is Hooke's law.
Yeah,
Now, this entire damping thing works on Hooke's law. That wherever there is a force being applied, then it will have a constant k and then it will have a certain kind of displacement occurring. Now, every time this damped harmonic motion is occurring, there is major reason for this damping to exist is the friction of the air that is causing the damping nature. Like suppose the sound vibration. Last day we saw that when the person actually increased the sound volume, then the woofer started making a certain kind of, very high kind of sound, which was also cutting the air friction and then it mixed with that air friction, producing a different kind of sound. That means if we would have been in a place where there is no air friction working, then the sound that would have reached our ears would have been different. In other words, that due to this air friction, the oscillation and the periodic motion is working. Otherwise, there would have been no damping. And as a result, due to the friction, what will happen to the motion or the amplitude of the sound that is being created?
it will gradually decrease.
Exactly, it will gradually decrease. So this certain reduction in the amplitude due to the work of friction, you can call it damping. Okay, that means
Yeah,
that the sound is getting damped. Clear?
yeah,
Now, in real life, damped harmonic motion, I already gave you the example of pendulum. It can be, when we were small, we used to play with small kind of gaming instrument that was like small one yo-yo. We used to just have a hanging elastic kind of string, and then we used to play with it. Do you remember that?
Yeah, yeah.
So yo-yo is also again a kind of damp harmonic oscillator which produces damped harmonic motion. And one of the greatest examples is guitar string. Because guitar string creates such kind of damped harmonic motion. You might have seen that every guitar has got a hole in the middle, right?
Yeah.
Now, every guitar has got that hole in the middle because this damped harmonic motion works there when each string is strummed. If that hole
Re-
does not exist, the guitar will not sound as it sounds.
really? Like, cause
Exactly.
it echoes inside and like the
Yes.
sound.
Exactly. It hits the inner side of the guitar, which is totally filled with air because you cannot create a vacuum there. And that is again coming back to our ears with the damped frequency. Due to that
Mm.
reason, it sounds so much different. Every time you if you touch a guitar string every time in a different manner, it will produce different kind of music. Imagine if there would have been no hole in the guitar, it would have been sounding entirely different because there would have been no damped harmonic motion occurring there, right?
Miss, how's there damping in guitar?
In the guitar, I told you the hole, inside the hole, it is totally filled with air, right? So the air resistance is doing what? The string is producing a certain kind of tune, and that tune is hitting the inner surfaces of the guitar and then again coming back to our ears. So the
Miss,
guitar strings are moving in a periodic motion. Till the time the periodic motion continues, you will hear the damping sound. As soon as the periodic motion comes to rest, the sound will be gone. It's like ting, and then it stops, right?
yeah.
So that's the thing
Miss,
that's
so,
happening. Yes, please.
like if the damping occurs due to the presence of air in the inner
Mm-hmm.
portion, then
Mm-hmm.
like that air is even like outside, right? So
Yes.
there'll be damping outside as well.
Yes, outside air is also interacting, but the inner air is producing that kind of vibration, which is actually allowing the guitar to sound in a very different manner. If you look at different kinds of guitars, suppose, have you seen different kinds of guitars? The one that we are particularly talking with the circular hole, that is, in general, the acoustic guitar,
Yeah.
right? So we majorly see the acoustic guitar only, but there are different kinds of guitars. And if you notice different kinds of guitars, every different kind of guitar is having a different kind of pattern. Not every guitar is having a hole. Okay. The one that I'm talking about, a acoustic guitar, that's why acoustic guitar sounds very decent. All the other types of guitars, they are very different in the tune. For example, you take a guitar that is played in a rock band. They usually play electric guitar which is not having a hole in the middle. Okay,
Yeah.
so that sounds entirely different. Are they using different kinds of strings? Not precisely, but yes, they use some different kind of strings as well. Not all of them are different, but yes, some different kinds of strings are used. Classical guitar, it also has a hole, but not a bigger one. It has got a smaller one so that the damping effect lessens down. And acoustic guitar is the one that is having the bigger hole. And ukulele has got a hole because ukulele sounds more like acoustic guitar only. If you take mm, even a semi-acoustic guitar, that will not have a hole because that is not allowed to give that kind of a pattern of music. So that's why these, and electric guitar doesn't have a hole. Yeah, it has got a hole, but not particularly in that particular position. Some holes are there inside inner position. So that produces entirely different kind of sound. Okay,
Mm-hmm.
clear now? Every different instrument is having a different kind of nature so that it gives out a different kind of music, because they're not changing the every string or like that, because every string is of different thicknesses that produces a different kind of music. Okay.
Right.
Okay. Now, coming to the thickness of the string that actually changes how the damping will happen. Now, why do you think that changes?
Miss, because uh, there are different frequencies or different amplitude.
Yes, that's also true. It's of different frequency and different amplitude, as well as the displacement will be different for each of them. For example, if I take the thickest string of the guitar, that is thick
Mm.
in nature, but I am hitting it with the energy that I have, right? So let me consider that my energy is constant. So if my energy is constant, then the displacement that is happening for the thicker string will be less than the one that is happening for the thin string, right?
Yeah, yeah.
So that is also again affecting the entire damping thing, right? Because as I told
Because,
you, it is dependent on the Hooke's law.
yeah, displacement.
Yes. Got it?
Yeah.
Now, again, if we talk about this displacement, do you remember the displacement formula for harmonics?
No.
Okay, let us go back to it. X is equal to A cos omega t. Have you seen this formula before?
Yeah, this one.
Yes. Now, omega is what?
Uh, Omega is, I think, yeah, I forgot.
It's angular frequency, okay?
Yeah.
Omega is equal to angular frequency, and it is also equal to 2 pi f,
Mm.
where frequency f is the natural frequency of the oscillation that is happening, okay?
Right. Yeah.
And a is in general acceleration, as we know, t is time. So this is the formula for the x value that we were talking about in the Hooke's law, and this is directly correlating the entire thing to angular frequency, right?
Yeah.
Okay. So now, coming to my point, if this is such a situation happening, now what if we add some fluid around the ball? The ball was attached to the spring. Now, if I'm adding certain kind of fluid around the ball, then what will it
Around or
experience?
miss
Yes,
around or
maybe I'm
inside?
dipping the entire setup inside some water containing container. Okay, then what do you think will happen?
Mm, miss then it'd be more damping because the weight increased.
No, in air it was easier for the ball to move. Inside water, it will be restricted somehow, right?
Oh, the whole thing is inside the wall.
Exactly.
Okay, okay. Yeah, then there'll be a lot of resistance.
Exactly. Because of buoyancy of water, again, the entire setup will feel a certain kind of burden on it. And then, again, it will also depend upon the viscosity of the fluid. If I'm considering water, there is a buoyancy. If I take a more viscous kind of fluid, then again, the damping will be even less, right?
Yeah.
Now, if I have such kind of damping happening, then my entire formula is also going to change, right?
Mm, yeah.
But what will be the factor that will be introduced inside the formula then, that will be influencing particularly the ball and the damping?
Miss, like you said, viscosity or density.
That is for the liquid. I'm talking about the ball. Because when we are going through the Hooke's law, we are actually talking about the ball using the spring equation.
Then it'll be displacement.
Displacement, right? So if displacement is working, that means directly the velocity is changing. Because the velocity of the ball will differ due to the buoyancy of water, right?
Mm-hmm.
Before it was like easily able to vibrate. But the velocity will change. It will become slow because it is not able to move through that particular displacement. Displacement is already existent in our formula. We require something that will give us the effect of the change that is happening within the setup. Otherwise, there would have been no difference in the formula, right?
Yeah.
Before, it was force is equal to negative kx. Right now, it becomes force is equal to negative kx minus bv. V is for velocity, B is a constant that will keep on changing depending upon the viscosity of the liquid. Every liquid will have a constant B value. Okay.
Miss, what's the name of this constant?
There is not any particular name of the constant. It is just a constant used for damping equations only. So there is no particular name of this particular constant. It
Okay.
is just proportionality constant for the velocity of the ball with the force under very special condition. I already told
Mm-hmm.
you what the condition is, right? Now, if
Miss, could
such
you,
kind happen, yes, sorry,
Miss, could you repeat that condition?
yes, sure. See, this constant is only dependent upon the special condition that we are facing right now. That is for this situation where we are dipping the entire setup that was there inside the fluid that we are having. I was talking about water as an example so that you can understand. But
Yeah.
it
Okay.
it can be any other fluid. Sometimes it can be water, sometimes it can be something else, right?
Miss, so like when the ball is attached to a string, right? So the
Hmm.
length of the string would also, you know, like change displacement, right? If it's a shorter
Yes,
length, it'll
yes,
have
definitely,
less.
definitely,
So,
definitely.
so Miss, why isn't the length of the string in the equation here?
Not strings, spring.
Or spring? Sorry.
Yes. So the thing is that for every spring, the arrangement would be different, right? Every
Yeah,
spring will not have this particular arrangement, and the force that you are applying, that spring will have a k value of its own. That's why we are taking kx. What
right.
is
Yeah.
k in Hooke's law? Do you remember what is k in Hooke's law?
Oh no.
That k value in Hooke's law, the positive constant that we use, that is the spring constant.
Right.
Okay.
Yeah.
The spring constant varies every time you change the spring because the spring constant is dependent upon the variety of string, material of string, the length of string, everything. Remember now?
Yeah. Yeah.
So definitely we are having the spring thing as well. That's why we don't need to worry about that. Every time we are changing the spring, the k value will be changing. Totally. Clear?
Yeah.
Okay. Now, because of the result of this thing, do you think the x equation that was a cos omega t will change if I'm using another variable here that is velocity?
Mm, yeah.
Okay, then how?
Uh, because now velocity is also coming under consideration.
Okay, yes, there comes a value of decay because the amplitude that we were having before, let me give you another one. Yeah. Let me show you a graph. This is a situation that is happening with the situation that we are having right now. If I dip the entire thing inside a fluid, you see the amplitude that was present towards the starting, it slowly decreases to become zero, right? Because the wave is diminishing to end up sometime. Getting
Yeah.
it? Now, when the wave is ending itself, that means it's decaying to become zero.
Yeah.
This decay is very similar to nuclear decay. If it
Miss
is
nuclear
large,
decay,
mhm,
like that's formed by splitting atoms or combining,
yes,
like when
yes,
two
that
nuclei
one only.
combines. Yeah.
Yes, exactly that one only.
How are they similar?
Yes, it's very similar to that. Not exactly the same, but very similar to that. Now, scientists thought that we can combine these things together to form an equation. So, this BV value was then considered as the drag force. Okay, the
Right. Yeah.
drag force, the what is drag force? Do you remember?
Yeah, it's the resistance.
Yes, it's the resistance, mostly the frictional force related to the drag. So that's the drag force, and drag force is again dependent upon the density of the fluid and those things. We did not go there right now, and we also don't have it much. So coming back, so if it's a more viscous kind of a fluid, then definitely the drag force will be greater, right? Then
Yeah,
if the drag force is getting greater, what will happen to damping?
it'll increase.
It will be heavy, like those if someone is using a bass instrument, right? It's heavy, right?
Yeah,
It's not moving with a greater frequency, still it's heavy, correct?
yeah,
Now, if suppose the mass is coming back to its own position, that is, it comes quickly to an equilibrium position, then what will happen if such heavy damping is occurring and suddenly the mass returns to its equilibrium position?
then I don't, without even completing one oscillation, if it comes back, then it won't come under this, will it?
No, it has to complete one oscillation. See, without completing one oscillation, that's practically not possible. Because if it is moving like this, it cannot come back to suddenly this position. It will move back to it. Even a little bit, it will move back to its means the oscillation, because that's the nature of the motion. The oscillatory motion will never stop itself in the middle because there is also gravity working, right? If it goes up, it needs to come down. Or if it's coming down, it needs to go up a little bit because we have applied a force on it. We cannot defy the nature's law, right?
Yeah,
So that will never happen. Yes, it might happen that after completing one oscillation, suddenly it comes to a certain kind of mass equilibrium due to the viscosity of the fluid and it is no more able to produce any more oscillations. But at least one oscillation will be there, okay? Because you have applied a force. If there would have been no force applied, it would have been at rest, then there is no issue for the oscillation, right?
yeah,
Now, if the fluid is very viscous and still you have applied force, the oscillation might not even happen. Like you have applied force, but the mass is not moving. That time there is no acceleration occurring. But if it has started oscillation, it will complete one oscillation. You cannot have half oscillation. Clear?
right, yeah,
Now, if the mass returns to the equilibrium situation, this damping is known as critical damping. Okay? You can write it down. It is known as critical damping when the mass will return to its equilibrium position as quickly as possible. Means the least number of oscillations will happen.
Yeah.
Okay. There is another situation which is known as overdamped, where the system is moving towards the equilibrium situation, but slowly. In critical situation, what happened? It immediately came back to its equilibrium situation, completing the least number of oscillations. But in overdamped situation, the damping is heavy, but still it is taking its own time to come back to its original equilibrium situation. It's like you went for a wedding and then there the food is not good. You won't have much of your energy to go to the food stalls. You will just eat few of them and then you'll come back, right? But suddenly, if you go to a wedding and there is like, the menu is, oh my God, like all the tasty foods over there, which you like. So definitely you will take a greater time over there. So the same thing is happening over here also. Very similar thing. If it is coming back immediately to its equilibrium situation or with the least amount of oscillations happening, it is known as critical damping. And if it is taking a longer duration of time to come back to its equilibrium situation, moving slowly, creating maximum number of oscillations, then it is overdamped. Clear?
Miss, why is
Mhm.
it termed as overdamping? Because the more damping it would be, the lesser
Yes.
oscillation.
No, heavier damping is happening. That's why. And more number of oscillations. That's why it is named as overdamped. Nothing as such. The name is not related as such to any other thing. Okay.
Okay.
Now, till now, we have seen that the vibration was occurring on its own. We need not have to force the vibration to take place. Means we are applying some force on the object, that is the mass that is there. But we are not applying, means forcing the entire oscillation to happen, right?
No, only at the beginning.
Exactly. Have you must have ridden bicycle, right?
Yeah.
Bicycles have springs. Have you seen that? It's holding it whenever you're
Yeah.
paddling, then it's riding through your paddling wheel, and then those springs are adjusting themselves so that you don't fall down or the cycle doesn't suddenly stop. That's why whenever people who experience breakage in the spring, suddenly they can fall and immediately have a bad accident, right?
Miss Spring is present in which part of the cycle?
Precisely, the springs that is present in normal bicycles is near the region where you're paddling, the region between the paddle, the wheel that is attached to the paddle. In that region, there is a small spring there on both sides, of course. When you're paddling, the
So,
spring is bouncing.
and okay,
In
and
case of
so,
geared cycles, it is different because geared cycles change their gears every time. So they have a different spring arrangement inside them.
mm-hmm. So that prevents us from like it. It lets the wheel continue to rotate and let the paddle like stay still.
Yes, kind of shock absorber kind of thing. So that because when you're pedaling through it, then you're creating a large amount of you know mm, force on the cycle. So it needs to adjust through that force, right? Otherwise, it
Yeah.
will just move on randomly. So that spring is kind of shock absorber kind of thing. It is adjusting the force and then distributing within the entire cycle itself. Okay.
Right.
So now, when you have such kind of an oscillatory system, which is having certain kind of a mass on the spring and that is distributed, everything will oscillate in its natural frequency, right? And what will be the formula for natural frequency in that case then? If we are talking about the mass attached to the spring in that sense,
The formula for natural frequency.
yes, in such kind of a condition.
I'm not sure.
Okay, no worries. Uh, okay. There, the natural frequency is going to be dependent on the spring constant. Okay, the spring constant, that is K, root 2 pi root over A by M. Sorry, 1 over 2 pi it will be. Natural frequency we are talking about. Now, you might have seen this formula in a different manner because you might have seen it for time period. And this is for frequency. Have you seen this formula before?
Yeah, I think
You might. Because it comes from the same, the pendulum time period formula. From there it comes.
Mhm.
So this is nothing, just we are introducing the K factor over here where the spring constant is being added.
Right.
Okay?
Yeah.
Okay. Now again, when we are applying this certain kind of natural frequency and then there is a force being applied, different kind of speed keeps varying, then the natural frequency of this entire mass spring system, it will keep on varying and the amplitude also will keep on varying according to the frequency, right?
Yeah.
When the amplitude is at its peak, then the driving frequency becomes equal to the natural frequency.
Nice. What does that mean?
How does it happen? First, let us understand how does it happen, right? What is
Yeah.
driving frequency actually? What can be anything that is like acting like a driving frequency?
The one which ensures that the frequency remains the same.
Exactly. The one that is actually making the oscillations happen, right?
Yeah.
That is the one that is driving the frequency. That means the
Yeah.
force that is being applied. Uh, in case of, if we take the cycle example, you are pedaling the cycle. So you are the one that is producing the driving frequency, right?
Yeah.
So there will be a situation when the natural frequency amplitude keeps on increasing and that natural frequency amplitude reaches to its maximum level when it is equal to the driving frequency. Okay.
Mm-hmm.
So that kind of situation is known as resonance, where the driving frequency is close to the maximum natural frequency, where the amplitude is at its peak.
So it
That
can't
is
go beyond that.
certainly no, because natural frequency has reached to its peak, right? Amplitude has reached its peak. So beyond that, it's not possible. You might have seen the equation of A max there. What is the equation of A max?
Don't know.
Based on the omega formula, what is A max? You have read it, okay? Go through the formulas once. Actually, it will be helpful for you. Do you want the formula chart or do you have it?
Miss, can you please share it?
The formula chart.
Yeah.
Okay, okay, I will share that with you. All the formulas are there, like A cos omega t. We have not taken into consideration here the theta values. So that's why it's not here. But in this case, if we are taking the A max value, that is the, yes. If we are taking the A max value, that is the maximum amplitude over here, that is equal to F naught d omega. Okay. B is again the constant coming from the drag force, and F naught is the initial frequency, you can say. No, sorry, not initial frequency.
Driving
The
freak.
force, the initial driving force, right? It's the driving force because the driving force is actually changing till it reaches the driving force. That's why this is the driving force that we are talking about. And omega is obviously, we know what is omega, right?
Yeah, angular frequency.
Yes. So now that we have reached till resonance, let us know more about resonance. If we are having a normal, very lightly damped system, then the resonance frequency is almost equal to the natural frequency. But if the damping is heavier, then what do you think will happen to the resonant frequency?
It will decrease.
Exactly, it will decrease. And just the opposite situation, if it gets lower, then it will increase, right?
Yeah.
So, if we try to make this into a graphical representation, you will see there will be a tremendous change. Let me show you how. Do you see this?
Uh, where
The
is it?
change is, yes.
Miss, did you
Can you,
put it?
wait, yeah, can you
Okay,
see
yeah,
now?
yeah. Yeah.
Yes. Now you can see that when's the frequency, how drastic change is there. With heavy damping, it is so low and the amplitude is very light. And whereas with light damping, the amplitude is so high because it is reaching towards the maximum natural frequency amplitude, right?
Mm-hmm.
So now we absolutely know that how the driving force is actually affecting the entire thing that's happening, right? Because the
Yeah. Yeah.
driving force is the one that is providing the energy to drive the entire system, right?
Yeah.
So that means damping reduces the maximum amplitude and the resonant frequency of the resonating system.
Yeah.
Yeah. Okay,
Miss, I have a question.
sure.
Miss, over here, why is frequency like that?
Mm,
Like,
that
why is it
means,
represented like that? Like, why is the frequency increasing? Suppose the red one. Why is the frequency
yes.
like suddenly increasing and then going down? Why is it not staying there?
Why is it not staying there? Sorry, I didn't get you.
Like the curve, right? The red one. So
Okay, why
it
did it suddenly increase? That's your point.
yeah, and why is it coming back down? Like, why does it not stay at two? Like at two,
Oh,
the
okay.
highest.
Why doesn't it stay at its peak, right?
Yeah.
It's a wave. How will it stay at its peak? It will come to zero, right? Ultimately, the destination is somewhere coming to zero. This frequency is not taken to zero because we cannot hear it, but that frequency is present somewhere, right? Till it vanishes.
Miss,
So, yes,
miss over here, like in this graph, the x-axis is frequency, right? So what is the y-axis?
amplitude. It's the
So,
amplitude.
so, miss, so why is the
Mhm.
frequency like changing?
Why will the frequency not change? The entire thing is about frequency only.
I mean, yeah, it does change because it's oscillating, but
Yes.
um, like it's
The way the frequency is changing. See, the change is actually happening in case of amplitude. If you look at the graph, The entire change is taking place due to the amplitude, and frequency will keep on changing as time progresses, right?
Miss, I thought frequency remains constant and amplitude keeps changing.
No, no, no. Frequency never will remain constant. The entire thing is happening surrounding frequency. Frequency can never remain constant. The only thing that will not remain constant throughout every situation that is happening is frequency. Because if frequency becomes constant, then no other thing is happening. No damping, no resonance, nothing. Okay?
Miss, so like,
You tell me one thing.
um,
If there is a certain specific frequency reaching to you, your ears will not be able to tolerate that particular frequency. If I play one sound that is having only one particular frequency, that is constant frequency reaching to you, the sound will be produced. You will hear the sound, but your ears will not be able to take the frequency. Will it?
Miss, I didn't
It
know
doesn't.
that. So it keeps changing.
Yes, frequency is every time changing. Even while I'm talking, I'm not talking to you at a particular frequency.
But like, suppose the keyboard, right? Or the
Right?
piano. If you
Yes.
play one key, that will be at a particular frequency, right? Or will
Yes.
that also keep changing?
See, the pattern that is whether you're pressing the key with low hand or you're pressing it directly, you're pressing it for certain duration of time, or you're just pressing and then removing your hand. Frequency depends on all these factors.
Miss, like,
They
suppose
have.
I'm holding
Mhm.
it.
If
Like,
you're
I'm
holding
holding.
it, yes, if you're holding it, that it will be at constant frequency. If you are holding it constantly, then it will produce a constant frequency. I'll tell you a difference. When someone is playing a piano or the keyboard, and if someone is playing the harmonium, the frequency will depend upon the bellow as well as the keyboard. But for piano and keyboard, you don't need the bellow. You only need to press the keys. So if you're pressing the key for a longer duration of time, you will not be able to hear that particular sound. Means you will hear the sound, but it won't be peaceful enough for you because it is coming out with a constant frequency. We don't require that.
Miss, that's not true because I play the piano and I mean, if you hold one key for a long time, I mean,
Mhm.
of course, the loudness decreases gradually, but it's not like you won't be able to hear it after some time or.
I'm not saying that your ears won't find it peaceful enough to hear that particular frequency for a longer duration of time. If there is a constant frequency reaching your ears will
Mhm.
find it not good enough to hear to that particular frequency for longer duration of time. You can hear it for some time, and definitely if that frequency is traveling after certain duration of time, it will cancel out itself with the interference that is happening due to the friction of the air, right? Because why does your piano produce the sound? First tell me this. When you're pressing the key, why does it produce the sound first?
Miss, I don't know, there's some inside parts, like some
Yes,
strings and.
exactly. There are inside parts present, and if you have noticed, your keys are not sticking to the surface, they're having a certain gap, right?
Yeah, yeah.
When you're pressing the key, that gap is no more there. When you're pressing the key for a long time, you're creating a vacuum there. If there is no airspace present, how will the frequency sustain? You need to create
Mm.
another frequency after pressing the key again. That's why, for a longer duration, if you're touching, when you said you learn piano, right? So, whenever there is a certain kind of tone that you need to repeat, you will press it twice. You repeat it and then you press it again, right? Because you know
Yeah.
after some time it will fade away because that air gap won't be there. That's the science behind it. You do it, but you don't know why you do it, right?
Oh, so that's why it like slowly over time, like it reduces the sound.
It will reduce and fade away. There is a
Yeah, but
purpose why the even your keyboard, the laptop or desktop keyboard that you are having, that is also having a certain kind of gap. See, it's
yeah.
not totally touched. They're not totally having that no gap spaces there.
So that's why. So like the loudness will decrease, but frequency will remain the same, right?
No, after certain amount of time, the frequency will also be gone because the air gap is then not there. Means it will stop producing the frequency. That's the thing. The
Oh,
instrument will stop producing the frequency. You can try it out and see. Just press the key of your piano. After some time, you will see that it is no more producing any frequency because you have pressed
okay.
it for such a longer duration of time. Now, if you press it again, it will again produce because till that time the air molecules have still entered the region, and then because of that, again it will produce the sound.
So it's all about air pressure.
Yes, kind of. It depends totally. They're independent, means they're independent in that sense, but they're dependent on each other for things happening. That's why you cannot hear anything in vacuum.
Uh
Got
huh.
it?
So I'll play. Okay, just like one key.
Sure. Understood the fading away?
Yeah, yeah. It does get kind of weird, like towards the end, because
Exactly.
it's one same frequency, right?
Yes, you can try and experiment this. YouTube, they have certain kind of such experiments, sound experiments. So
Uh huh.
now there are weird kind of sound experiments as well that do not have much to do with science, but there are few kind of frequencies that you will find. They say that this frequency will calm your mind and whatnot. I don't know. They have not done anything for me. Yes, but there are certain kind of meditation frequencies. If you just try to concentrate, if that will be helpful for you in exam time. If you use those meditation frequencies, you're studying for a longer duration of time, you take a 5 minutes break, hear to that meditation frequency, close your eyes and try to meditate. After some time, when you come back to the normal, it feels like, where was I? You will feel that, where was I? It feels like I was somewhere else in a place where there was peace. And then when you come back to study, you will feel the concentration level has increased.
Uh huh. I think those are like very ancient instruments. I don't know those.
No, not the instruments are normal instruments. It's just the frequency of the sound.
Oh,
Our
okay.
ancient people, they were way more advanced than what we are. So these things, like, even think of it, we at this age feel that we have kind of sleeping problems, right? I'm unable to sleep. I'm not getting sleep in time. These kind of issues are arising nowadays. But there are certain kind of meditations, frequencies, just music, nothing else. Just plain music. It will keep your mind calm and it will make you fall asleep. You'll not even know.
Mm-hmm.
So
Yeah.
these are few things that come from our ancient scripts and books. So definitely they were more advanced than us. We are having technologies. Definitely we are having technologies. But they are more advanced than us.
Yeah.
Okay, coming back to our resonance. Now, what you need to do is work on these formulas, okay?
Yeah.
Read your book and find out how resonance is acting. There is one more topic left in resonance. I think that will be a bit too much if I start it again now. Rather, you leave it here. One topic of resonance that will continue tomorrow. Oh, tomorrow, are we having a
Okay.
class tomorrow?
I mean, yeah, I can schedule one.
Yeah, ma'am.
Yes, sorry.
I said yes,
Ma'am, you
tomorrow
was. Oh,
class. There'll be a
oh, okay,
class.
okay. Okay, okay, sure. So, since tomorrow you don't have a school, I'll request you to at least read from your book the topics that we have discussed till now, or start
Yeah.
reading from the chapter from the starting so that you can get
Yeah.
a basic idea that what is happening. If you have any questions, keep it noted. We'll discuss in the in tomorrow's class, and this is the one last topic left for the entire chapter.
Yeah.
Okay,
Yeah.
sounds good. And try solving the questions so that at least if you are not able to do something, you will ask me, right?
Yeah, sure, miss.
You can read the book questions as well. Oh, yes, one last thing that I forgot to tell you, that was the open wave thing. We did the closed one, that both sides were closed. What if both
Yeah.
sides
Oh,
are
I read
open?
that.
Oh,
Yeah,
okay.
yeah, yeah.
You understood that,
And there's
right?
a different formula for it.
Yes, right. That's a different formula because if both sides are open, then the harmonics are going to change. And there you can see that the relation between the length and the wavelength both are again changing, and there the frequency is normal.
Yeah.
It's like F1, 2F1, 3F1, like that kind of. Frequency is not having any particular kind of equation there, right?
Yeah.
So this that one is easier. The closed one end closed and one end open, that one is a bit difficult one. And we have already discussed them, right?
Yeah.
Okay. Anything else you would like to ask from here?
No, miss.
Any other question arising in your mind?
No, miss.
Okay. Then what did I tell you? Take some rest, play some frequency, meditate a bit, and then come back studying again with fresh mind, right?
Yeah.
See, I gave you a way to relax your mind as well.
Thank you.
Okay. Okay, so tomorrow, when do you think we can have a class?
Miss, I'm not sure, but I'll surely let you know through
I'll
Oh,
let you
miss.
know.
okay, okay, sure. Thank you, ma'am. Okay, Shreya, then let's meet tomorrow. Let's end it here for today.
Alright, thank you, miss.
Okay, welcome. Bye.
Bye, miss.